What that allows us to do now is talk about continuity on a closed interval. So now we're going to be using endpoints that are there. So let's make a function. We're going to put it on a closed interval. Meaning the points are going to exist there. Okay. So this would be f of a, and then this would be f of b. So here's what it says. A function f, right here, is continuous on the closed interval ab if it is continuous on the open interval ab, so meaning all this inside stuff is continuous, which we figured out how to do on the previous page, and the limit as x approaches a from the right side equals f of a. Meaning, as we're approaching here from the right side, we can use direct substitution and find that limit of f of a. And the limit as x approaches b from the left side of f of x equals f of b. So the same type of idea. If we approach b from the left side, f of b is the same thing as our limit. Okay, so the function f is continuous from the right at a and continuous from the left at b. So that's what we would say about that function. So we can use that now to discuss the continuity of graphs that look like this. So we have the square root of 1 minus x squared on the closed interval, negative 1, 1. So we are using these x points, negative 1 and 1. So first off, is this continuous on the open interval? Okay, so if we plug negative 1, anything from negative 1 to 1 in here, we do get a value, so it is defined, and we can find all of those limits. So we know it's open on, we know it's continuous on the open interval. Now we're going to check the closed interval. So coming here from the left and from the right. So we do the limit as x approaches negative 1 from the left. Oh, is that from the left or from the right? Well, the arrow's coming from the right. So that's got to be a positive of our function, 1 minus x squared. Okay, well, looking at this, our limit looks like it's 0. And we set up here that it has to equal f of a. So whatever that value is. Here it's negative 1. So if I plug negative 1 in here, what do I get? So here we have 1 minus 0. The square root of 1 minus 0 is 0. So it does indeed equal f of negative 1. So that works. It is continuous from the right. Now we're going to check that it's continuous on the left. So we're taking the limit as x goes to negative, or let's see, now we're going to this point of 1. And this is going to be from the left side, so we're going to put minus. Then our function. And we can see this is also going to 0, so we know that's the limit. And now we're going to check if we can use direct substitution. Square root of 1 minus 1 squared does equal 0. So because we can use direct substitution there, this is continuous from the left. All right, let's move on. So some properties of continuity, just want to share them with you. You can tuck them away as tools to be used later. So if b is a real number and f and g are continuous at x equals c, then the following functions are also continuous at c. So if we can just have two basic functions that we know are continuous at c, then we know these things are also true to be continuous. So if we have a continuous function that we multiply by a number, we know that it's also going to be continuous at c. If we add the two functions that are continuous at c, well, that function would also be continuous at c. If we multiplied them, same thing. So continuous function at c, continuous function at c, multiply them together, we would still have a continuous function at c. It also works for a quotient, okay, as long as g of c doesn't equal 0. Okay, then this wouldn't work. Okay, so some types of functions that are continuous at every point in its domain. So these are not functions that are always continuous, but they're continuous in whatever is in the domain. And so that's going to be polynomial functions, rational functions. So notice where q of x doesn't equal 0, because that wouldn't be in the domain. Any radical function, okay, as long as it's in the domain. So again, we can't have square roots of negatives, that sort of thing. And then trigonometric, as long as x is in that domain, it's going to be continuous. So notice things like tangent, they're going to have places where it's not, x is not going to be in the domain, so it wouldn't be continuous there. But if it's in the domain, we know it's continuous. So really all you would have to check there is the f of x. All right, continuity and composition of a function, that's basically what we were talking about up here. If g is continuous at c and f is continuous at g of c, then the composite function f of g of x is continuous at c. So we want to discuss the continuity of the composite function h of x, okay, that's equal to f of g of x. So really what we want to do here is just come up and figure out what h of x is equal to. Okay, so it's f of g of x, meaning we're going to take g of x, we're going to substitute that in for x right here. Okay, so we can get something like 1 over the square root of x minus 1. Now we want to talk about the continuity, so we need to find its domain. So it's got to be on the domain. All right, so the domain of this thing, we know we can't have a negative number in here, so any value greater than 1 is going to work. And we know it can't equal 1 either, because then that would give us 0. So the domain is x is greater than 1. Now because it's rational and we have a radical, we know that it's going to be continuous at every point in its domain. So what we're going to say here is it's continuous on the interval, we'll make this open, 1, comma infinity. All right, one last idea for today, something called the intermediate value theorem. And it states if f is continuous on the closed interval a to b, and k is any number between f of a and f of b, then there is at least one number c in the interval a to b such that f of c equals that k. Okay, so what does that mean? Let's draw a function here. And we're just going to say if this function is continuous on our closed interval a to b, that means if k is any number between f of a, right here, and f of b. So we can let k be anything between here. Then there's at least one value c down here where f of c equals k. So you can see if we take k and we come across here, we would get at least one c value or if we plugged it into our function, we would get k. So what this is really saying is a continuous function will take on all values between f of a and f of b. So again, it's just saying if we look between a and b, the function is going to take on all the possible values between f of a and f of b. So going in here, we hit every single one along the way. Okay, so if the function is continuous, we know that's true. So here's how we can apply it. It says verify that the intermediate value theorem applies to the indicated interval, and then find the value of c guaranteed by the theorem. And we want to add on one other question here. We want to show that f of x has a 0 in the interval. Okay, so first off, to verify that the intermediate value theorem applies, it means that f has to be continuous on the interval. So on the interval 0 to 1, is this function continuous? Well, it's polynomial, and 0 to 1 is defined on the whole way. So we do know that this function is continuous. And now we want to talk about this interval idea. So what we're going to do is we have our interval 0 to 1, and we need to substitute that into our function. So we're going to find what's going on at f of 0, and we're going to find out what's going on at f of 1. Okay, and notice these two values here are going to correspond to these two values right here. Okay, so that's what we're finding right now. So f of 0, 0 cubed plus 2 times 0 minus 1. So that just equals -1. Then f of 1 would be 1 cubed plus 2 times 1 minus 1. And that equals 2. So on this interval, 0 to 1, we know that it goes from -1 to 2. So graphically, let's just kind of see what happens here. So here is our interval going from 0 to 1. And it's saying that this function is continuous, and it goes from -1 right here all the way up to 2 up here. So this is sort of like putting pieces of the puzzle together without actually seeing the picture. So the question is, show that f of x has a 0 in the interval. Okay, so if we start here at -1 and we end here at +2, and we know this function is continuous, okay, what does the intermediate value theorem tell us about the function? Well, it tells us that it equals every possible number between -1 and 2. So at some point along the line, will the function equal 0? Okay, so will the function ever equal 0? Will it ever cross this line? Well, yes, it has to. Without even knowing what this function looks like, okay, we know it's going to cross right there. So how are you going to write that mathematically? You're going to do this. You're going to write f of 0, so our left interval, is less than f of c is less than f of 1, which is our right interval. So our f of c equaling 0 has to exist on that interval. So we just write a0 exists. Now, if we want to find the value of c guaranteed by the theorem, we know it exists. So we know the 0 exists. Let's go ahead and find it. So we want to know, where does that function equal 0? Now this is a cubic, and it's not going to be so easy, because even if we factor this, even if we add the 1, we get something like this. All right, we really have no methods for solving this. So what we can do, since it's asking us to find it, is we can use our calculator to find that 0. Okay, so go ahead and take out your calculators. And we want to put in the function x cubed plus 2x minus 1. I'm going to go ahead and hit graph. Okay. And you can kind of see we got kind of close. And you can see between 0 and 1 that it is continuous right there, and it does cross the x-axis. Now to be able to find the 0 on your calculator, you're going to go second and calculate. So second calc. And then you're going to select 2, which is 0. Now it says, what's the left bound? So we want to go to the left of the 0, and so we're already there. And then to the right bound, just anywhere to the right of it. And then it asks us to guess. So we're just going to put our cursor close, and hit enter. And here it approximated our 0 at 0.453. So here x is approximately 0.453. So our value of c, which is guaranteed by the mean value theorem, is 0.53 approximately.